Good morning, guys. These are notes on the standard deviation of both a population and a sample. Standard deviation is the most commonly used measure of variation in statistics. That, along with variance, are the two primarily used measures of variation, but standard deviation is definitely the most used. And like mean, we do differentiate between finding the standard deviation of a population and finding the standard deviation of a sample. And they have a little bit different notation. And like usual, we're going to have to make some edits to the notes. There are a couple of mistakes, so bear with me on that. Here we go. As far as standard deviation, if we just break down that phrase, I guess you would call it, the two words, we have standard, what is expected, standard in the industry, and deviation, we're departing from something, a departure. So the expected departure, and in the case of standard deviation, it's the expected departure from the mean. So if we were to choose any data point from a data set at random, how far from the mean should we expect it to be? That is what we're talking about with standard deviation. Let's look at this little simple example. This is a two-value data set, and the numbers the values of the data set are 3 and 5. All right, so obviously the mean or the balance point of 3 and 5 is 4. So in this two-value data set, if you were to randomly choose one value, how far would you expect it to be from the mean? And I think it's obvious that you would expect it to be 1 away from the mean. You only have two choices, 3 and 5, and they're both 1 from the mean. Simple version, or a simple way to visualize what standard deviation is. How about another two-number data set, this time a little more spread. The numbers are 2 and 6, but again, the balance point is 4. So we have two data sets with the same mean, but as you know, the measure of center doesn't tell the whole story. We need to look at more things in a data set, like variation. How about the standard deviation? How far from the mean would we expect a randomly chosen value in this two-number data set to be from the mean? And again, I think you can see that it would be 2 away from the mean, both 6 and 2. So if we were going to try a calculation of the standard deviation at this point, we might take the difference between each individual data point and the mean, add them together, and divide by the number of numbers. So let's try that. If we take 6 minus 4 and get 2, and take 2 minus 4 and get negative 2, and we add 2 and negative 2, we're going to get 0. And 0 divided by 2, well, we know what that's going to end up being. 2 is the number of data points. We're going to get 0. So that's not going to work. Intuitively, you might think that, but we do have a problem with the differences, or the distance from the mean of every single data point should always balance out. They should always end up being 0 when you add them up. So we're going to need another method, and that's what we're going to look toward here. Let's take another attempt. So this is calculation attempt number 2. We have a 3-number data set, 60, 70, 95, with a mean of 75. We're dealing with a population here. Remember, mu is the mean of a population. And in the far right column, we have x minus mu, giving us the difference between the individual data points and the mean. And we have the absolute. We're going to take the absolute value, so maybe that'll fix that problem of of adding up all of the differences and having it be 0. So 60 minus 75 is negative 15, but the absolute value of that is 15. 70 minus 75 is negative 5, but the absolute value is 5. And 95 minus 75 is 20, and that's positive already. We add those up, we get 40. And if we take 40 divided by 3, it's 13 and a third. So that's a better estimate of the standard deviation. of the three numbers, 60, 70, and 95, but it's not great. It's not perfect for reasons that are beyond the scope of this course now. Absolute value is a non-algebraic function. We need something to be algebraic. We want to deal with smooth curves. Absolute value, as you remember, has a sharp point, and that creates a problem when we extend the idea of standard deviation into more complicated formulas and procedures. So we have to do a little bit better than using the absolute value, though it's not bad. And by the way, that's called the mean absolute deviation. So let's get to the real deal. This is the formula or the calculation process for finding standard deviation. Once you know how to do this process, you're not going to have to do it by hand again, but you know how it works, you know how it's built, so you know what you're looking at when you calculate standard deviation with a calculator. Okay, same data set, same mean. The middle column here is individual data point minus the mean, so there's those raw differences. You can see the sum of those is 0, as it will always be. This time we're going to square those differences, so that'll take care of the negative problem, and then we'll come back and deal with that when we take the square root of the final result. Okay, again, we're dealing with a population here. Negative 15 squared, 225. Negative 5 squared is positive 25, and 20 squared is 400. We sum those to get 650. We divide that by 3, the number of values in the data set. And we finish it off by taking the square root, which reverses that process of squaring that we did there. Okay? And we use lowercase sigma to denote standard deviation of a population. Okay? There are some typos in the formulas on the next page. So what I'm going to have you do is write the two formulas here for the standard deviation of a population and the standard deviation of a sample. Here's what we did. Lowercase sigma, standard deviation of a population, is equal to the square root of, since we did the square root last. We are going to take the sum of the differences between each individual data point and the mean, so x minus mu, and we squared those differences. That's what that last column was, the differences squared added together. And we divided that by the number of values in the population, or the population size, so we need a capital N for that. Okay, the standard deviation of a sample is a lowercase s, is equal to the square root of the sum of any individual data point minus, it's still the mean, but this time it's the mean of a sample, so it's x bar. We square that. But this time we're going to divide by, well, lowercase n for 1 because it's a sample. But we're going to subtract 1. And you'll see on the next page that we don't really need to worry about why we're subtracting 1, but suffice it to say that if we did not subtract 1 with a sample, it would be an underestimate of the true standard deviation of the sample. So moving forward, as I said, we have a minor problem with the formulas, and that is that they're missing the capital sigma here. You want to try to squeeze that in between the radical symbol and the parentheses. There should be a capital sigma here and right there. Because remember, we have to sum all those differences squared. And this is basically saying that if we subtract 1 from the sample size, it provides an unbiased estimate of the population standard deviation. If we don't do that, it's a biased estimate. We could use some calculus to prove that. All you need to remember is that there will be a different standard deviation for a data set depending on if it's treated as a population or a sample. So we do have to know that. Okay. Moving on, we have ourselves a sample, body mass indexes. It's a 5-number sample. Okay, I'm going to have you find the mean and standard deviation. I want you to pause the video and try to calculate them, and play it again when you have an answer. If they match, you're good. If they don't, let me know. Go ahead and pause now. So the answer to the mean is 25.56. Remember, one place after the decimal more than the data set. And the standard deviation, lowercase s for a sample here, is 5.38, also rounded to one place more than the data set. Questions? Let me know. Take care.